Okay, welcome everybody. This is Wallace Sharif. This is our Morehouse College Bio 111 lecture. And we're going to start on thermodynamics and enzymes. Um, this is my first time doing this, so I'm kind of experimenting with this, as are we all. But this should correlate with the lectures that I've uploaded onto Blackboard. So we're going to talk about energy and flow of energy in living systems. We're actually going to spend about 3 chapters doing this. So this chapter, a chapter on cellular respiration and photosynthesis. And I want to kind of keep that in mind before we really get started. Um, on Earth, as we should know, the source of all energy is the sun. And the energy of sunlight gets translated into chemical energy via photosynthetic organisms like plants or, photosynthetic bacteria, right? Um, and so these organisms are called primary producers because they translate the energy of the sunlight into chemical energy that heterotrophic organisms like us can use. It's kind of remarkable, and we'll talk about this when we talk about photosynthesis, that these primary producers make enough chemical energy not only to feed themselves, but also manage to support all life on the planet. So we'll talk about photosynthesis. I believe that's chapter 10. And then we'll go into cellular respiration. I believe that's chapter 9. Now, we're going to go in this order because this is the order of energy from the sun. I don't know why the book flips these around. I'm sure there's some pedagogical reason, but we're going to go in this direction because it makes sense to us. And so ultimately, we take this chemical energy and we convert it into stuff that we can use to move our muscles and to study by biology and things of that nature. So before we get into living systems, we have to do a little bit of physics. And physics is obviously the foundation of chemistry, and chemistry is the foundation of biology. So we're going to have to back up a little bit and talk about work, what energy is, and then how we use both potential and kinetic energy. And so energy in a physics sense is the capacity to do work or to change, and work is moving things against an opposing force. In biological systems, as we said before, we'll do this looking at photosynthesis and cellular respiration. So for our purposes, energy has 2 forms, kinetic energy and potential energy. Hopefully we remember this. Kinetic energy is the actual energy of movement. And so here, this is the fluttering of a hummingbird. This is the fire, heat from fire, or this guy riding a bicycle over here. Potential energy is the capacity to do that work. And most of the food that we eat is potential energy. We break down that food in order to pull the energy out of those compounds and use them to do work. For us, and what we'll see in cellular respiration, is that we're going to take the energy of sugar and convert it into, well, break it down in carbon dioxide, water, and then store the energy that's produced in the form of ATP that the body uses to do work. This ATP is basically currency. You can consider it batteries or money, depending on whatever your favorite analogy is, um, that allows work to occur. And in biological systems, a lot of that energy is going to be in the form of concentration gradients. We'll see in cellular respiration that the buildup of a proton gradient across the inner membrane of the mitochondria um, is what allows ATP to be formed from uh, the process of oxidative phosphorylation. So that's basically all of chapter 9 right there. Here, I kind of put a classic example of potential energy, and that is in the form of a dam, a hydroelectric dam. You can kind of see that here. And what happens is that we, as humans, block the flow of water downhill. So this would be water coming from a mountain or something like that in a river. If we block it, that water, oops, wants to go downhill, but it cannot because of that wall. And if we open up chutes that control that flow, and that's over here, the water will come down. We can use the energy of that downward flow of water to drive a turbine. That turbine spins and powers electricity that we then use to uh, charge our cell phone batteries or play video games or whatever. And so the water behind this dam is a high source of potential energy. It gets converted to mechanical energy at the level of the turbine, which then gets converted again to electrical energy in the power grid. And so that's an example from physics. We're going to do a similar example using concentration gradients to do the same thing. So as I said, food is a form of potential energy. And the energy is really in the bonds that hold together the elements. And by breaking those bonds, we can release that energy and capture it in the form of ATP or some other molecule. And so to do this, we're going to kind of look at kind of classic thermodynamics. Thermodynamics, as you could probably break down, means what? Thermo here is energy, dynamic is to change. And so we're looking at the change of energy from one type to another. And biological systems follow the same rules of physics that every other system does. And so they follow the laws of thermodynamics. The first one being that we cannot make energy. The amount of energy in the universe is fixed. The only thing we can do is change it from one form to another. The second law of thermodynamics says that every time we do one of these transformations, we're going to lose some of that energy, at least in terms of workable energy. All right. So in biological systems, we lose that energy as heat, and this is something that we can't use to do work. And so that's summarized here, the two laws of thermodynamics. Here we see this block represents energy. We can do all sorts of transformations. Oops. We can do all sorts of transformations to that energy, right? But the total amount of energy must stay the same, and we will call that total amount of energy enthalpy. And the second law says every time we do a transformation, the energy that's available to do work decreases, and there's energy that we can't use or access, which we call entropy, that builds up. And so you can imagine, the kind of glycolysis, which is the anaerobic breakdown of sugar, uh, is a 10-step enzymatic reaction. Each time we do one of those steps, we lose a little bit of the energy that's available to do work. The total energy here has not changed, right? But the free energy, which is available to do work, is gradually loses. So you can liken this to an energy tax, right? When we go out and buy our, um, you know, Yeezys or something, right? We pay $200 for it, but we still have to pay another $20 that doesn't go towards the purchase of the shoe. It goes to the government or whatever. And so it's the same thing here. This process, the second law of thermodynamics, is why we have to eat in order to survive. We are constantly converting the energy that we have to this unusable energy or entropy, and we need to get a fresh supply of new energy in order to keep our biological processes going. So we can quantitate this, um, and we aren't going to go deep into this. We do in biochemistry, which you'll take in a couple of years, but we can kind of quantify this in a formula that simply says what we said before. Here, the total energy H is equal to the amount of energy that's available to do work, and we call that G because it's for Gibbs free energy, uh, plus the uh, uh, amount of unusable energy, entropy, that is a function of temperature, T. So that makes sense. The total energy must be the energy that's available plus the energy that's not available as a function of temperature, right? Since we're usually interested in G, we can rearrange this formula to simply say that the free energy, G, is equal to the total energy minus the entropy, right? And since we are interested in these closed systems, we kind of say that to say the delta or the change in entropy is equal to, or sorry, the change in energy, free energy, is equal to the change in enthalpy minus T delta S, which is the change in entropy. Now, this formula is really, really useful because by organizing it in this way, it gives us an immediate readout of the nature of a chemical reaction. So immediately we can say that if something increases the entropy, right, the delta S term is going to be larger, and so the delta G will be negative. So we know that when the delta G is negative, then the delta S is increasing, and this kind of follows the second law of thermodynamics. Um, and a negative delta G therefore indicates an exergonic, I don't know how to spell, shoot, exergonic reaction, and one that is a spontaneous reaction, which means in our purposes, it doesn't need any energy in order to go forward. On the flip side, if you have a positive delta G, then free energy is consumed, and that energy has to come from someplace. And so for this reaction to go forward, it must be coupled with an exergonic reaction. If the delta G is zero, you have a fully reversible reaction or a reaction that's at equilibrium. So the um, putting the formula in this way can kind of give us a readout of the nature of a chemical reaction simply by looking at the sign of the delta G, whether it's negative, whether it's positive, or whether it's zero, and it tells us something immediately about the process. And this is a kind of physical example of this. Here's an exergonic reaction balls up on a hill, and then it will, if there's nothing keeping it on that hill, spontaneously roll to the bottom of the hill, right? Every time you put a ball up that hill, it will. Now, we have to think about it. How does the ball get up that hill? Well, either somebody has to walk it up there, or the wind has to blow it up there, or whatever, right? Now, in chemical reactions, what this means is that the reactants have a high delta G, and then the products are at lower delta G, and that there is a release of energy in that chemical reaction. And so if we take something like glucose, C6H12O6, and it breaks down to CO2 plus H2O. Oops, I'm not going to balance this, but um, here, then here you have something that is complex and it gets more simple, and so there's a release of energy that's going on there. On the flip side, in dergonic reactions, this ball's at the bottom of a hill. Something has to get it up to the top of the hill, right? And so you need to put some energy into the system somehow in order for that to occur. Here, the reactants are at low energy, the products are at higher energy. You need to add some energy in order to do that. Now, in biological systems, a lot of times these are called anabolic reactions, and they are the buildup of uh, polymers from individual monomeric subunits. And so, anytime you take individual amino acids and make a protein or polypeptide, this is an anabolic reaction that takes energy in order to do that. Okay, so we call exergonic reactions that have a negative delta G catabolic reactions. They break down complex things. And endergonic reactions have a positive delta G. They're anabolic reactions and they build up uh, simple things. And if the delta G is zero, you have a fully reversible reaction in which the chemicals are the flow from uh, reactant to product are equal. Um, and um, I think I will end this here to keep it relatively brief, and then we'll go into enzymes and biological macromolecules in the next unit. But just looking, this is kind of an example I like to use. Here is an example of G1P going to G6P. And if we went to chemistry and asked the curator there to give us a vial of 100% glucose 1 phosphate, and so this is just for our chemistry nerds, glucose is 1, 2, 3, 4, 5, 6 carbons, and glucose 1 phosphate has a phosphate on carbon number 1, right? Now, if we put this beaker, just left it out, and let it go to equilibrium. Let's just say we left it out covered for a week or something like that. When we returned, we would find that the mixture, the solution, would actually be 95% glucose 6 phosphate and 5% glucose 1 phosphate. So we started with 100% glucose 1 phosphate, and somehow we're left with only 5% glucose 1 phosphate. And notice glucose 6 phosphate is that the phosphate went from position number 1 and somehow went to number 6. We call that an isomerization reaction or a mutation, depending on uh, how technical you want to be. So once it hits this ratio, we could leave this forever and it would never change from this 95% glucose 6 phosphate and 5% glucose 1 phosphate. This is where we say that it is at equilibrium. Now, this is not to say that the individual molecules don't change, but it is that whenever a glucose 1 phosphate switches to a glucose 6 phosphate, glucose 6 also goes to a glucose 1. So it's at equilibrium, and we would never see a net difference once it's at that equilibrium. So here, uh, when we're starting with 100% glucose 1 phosphate, there is an energy that's pushing it towards this glucose 6 phosphate. That is that delta G. Now, if we were to take that 5% glucose 1 phosphate and isolated it, and left it in another beaker, we would see that in a week or however much time it takes, we would go back to 95% G6P, 5% G1P. All right. And so this will always kind of return to this ratio because it is a function of the nature of the chemical equation. And in biochemistry, we go really deep into the delta G, the KEQ, or the equilibrium constant, which is just the concentration of products and substrate at equilibrium, and then what that means for biological systems. But for our purposes, we'll just kind of leave that be. Okay, so this is the basics on the kind of physics and how that applies to biological systems. For the next little unit, what I'll do is talk a little bit about uh, how this works in biological systems and then what enzymes do and the role of enzymes. All right, look forward to seeing you next go around. Peace.